Okay, so it looks like at the end of the first part of this problem, I did a silly mistake on signs. It turns out that the results are reversed. So actually, this is the minus, and this is the plus. So that means this is negative 7.97, and this is positive 25.93, which makes that the min and makes this the max. All right. So yes, a lot of calculus, a lot of algebra, a lot of solving systems of equations, linear and nonlinear. But what are we doing anyway? I mean, this is about finding max and min, yes, but what's the picture here in comparison to what we did in the previous section, in the previous section we were given a surface and we consider the surface at its entire domain. We would find max, mins, or saddle points, right? In this case, notice we're not looking for saddle points. So let me give you a visual from GeoGebra. So let me turn off the light so you can see it easier. Okay. So this is the objective function, f of x, or f of x y equals x squared plus y squared plus 4x minus 4y. So that looks a lot like a paraboloid shifted some units along the x-axis and along the y-axis, all right? So now I need you guys to think about the relative extrema if we were looking at the previous method with no constraints. Do you see there's only a minimum, which is the vertex of the paraboloid, right? However, how is this different from this Lagrange multipliers? Well, so now we have this paraboloid that is subject to this cylinder, a cylinder of radius 3. Okay, so this is what happened. You see this kind of an elliptical intersection between the two surfaces? Well, this is going to be, the intersection is going to be given by this slanted, tilted ellipse, right, in space. So that means, check this out. So when we are intersecting, what's going on here? When we're intersecting, anyway, it's not working. Oh, for real? It's not working. Let me open it again. So open. Okay. So this time, when we see the intersection of these two surfaces, we're no longer looking at the entire surface anymore. So we're looking at the max and the min of the paraboloid, because if you look at it, well, this paraboloid is supposed to have only a minimum value, that is the vertex of the paraboloid. But how come do we have a max and a min? Because now we're restraining this paraboloid to this cylindrical region. So do you see this little surface that we see right here, bounded above by this tilted elliptical plane, if you will? Okay, so now we're looking for a maximum here and then a minimum there, which are these order triples, right? So you see, that's the minimum, that's the maximum, but that's bounded by a constraint given by the cylinder, creating this sort of a plane, actually restraining. That's what it does. That's what the constraint does. Restrain the domain or the for only a sector on the objective function. So that's what we're really doing. That's how this problem is different from 15.7. Otherwise, we would have just done finding the minimum of this by simply using the d-test, and we would have obtained only one single critical point. Use the d-test to verify that it is indeed a minimum, and it's not gonna have anything to do with this order triples. It's gonna be a different number. All right, well, so that's the picture of what Lagrange multipliers is about. Let's do another example. For the next example, let's increase the level of making it more interesting. So now we're going to minimize but a 3 variable function. So not just 2 variables, so 3 variables. So here is a function to minimize. F of x, y, z equals to 2xy plus 6yz plus 8xz is subject to the constraint x, y, z equals to 12,000. Let's see what this is about. Rather, let's see how are we going to go about this problem. Well, so let's write x, y, z. So let's write x, y, z minus 12,000 equal to our constraint g, but it's no longer going to be a g of x, y. It's going to be a g of x, y, z. Okay, so let's form the Lagrangian for this. L of x, y, z, lambda, that equals the objective function 2xy plus 6yz plus 8xz plus lambda, the constraint, times the constraint, x, y, z minus 12,000. Let's do the calculus for the Lagrangian function. So in this case, instead of just taking the partials with respect to y, x, and y, and lambda, we're going to take an additional partial, that with respect to z. So we're going to obtain a total of 4 partial derivatives, 4 first partial derivatives. So if we had, in this case, we have a 3 variable function, we do a total of 4. If we had a 17 variable function, we would have done 18 partial derivatives, an additional one with respect to lambda. Okay? So let's take these derivatives. The Lagrangian with respect to x, that equals 2y plus, right here, that's 0, and then that's 8z. And careful here, the derivative of x, y with respect to x, it's going to be yz times lambda, right? So plus lambda times yz. You might want to set it equal to 0 at once. L with respect to y, or Lagrangian with respect to y. Okay, careful. The derivative of 2x with respect to y, that's 2x. 6z. 0. And plus lambda times the derivative of the inside of the parentheses with respect to y, the derivative of y, which is 1 times xz, equals to 0. Lagrangian with respect to z, 0, 6y plus 8x, the derivative of z is 1 times the coefficient xy plus lambda xy. Also set it equal to 0. And lastly, let's differentiate with respect lambda. So the first 3 terms are going to go to 0. So differentiate lambda, which is 1, times the coefficient, which is this quantity inside parentheses. That's essentially the constraint. Right? So we have a system of equations with 4 equations and 4 unknowns. Well, so how are we going to go about that? Well, let's label this. Let's label. So 1, 2, 3, and 4. So number 1, let's oh yes, yeah, I forgot to write down that 0, so that's a 0, and let's call it 4. Yep. Alright, so the first thing we need to do is get rid of the lambda. However, do you see how we have 3 equations containing the lambda? We have the first one, the second, and the third one. So how do we go about that? Well, number 1, let's solve for a lambda for the 3 equations. That is 2y plus 8z plus lambda yz equals 0, 2x plus 6z plus lambda x z equals 0. And lastly, 6y plus 8x plus lambda xy equals to 0. Okay, so let's solve for lambda for the three equations. Lambda yz equals to negative 2y minus 8z. Thank you. Then lambda xz equals to negative 2x minus 6y. And finally, lambda xy equals to negative 6y minus 8x. So to get the lambdas by themselves in the three equations, lambda equals to, okay, let me factor out the negative as well. That's a negative 2y plus 8z divided by yz. Lambda equals negative 2x plus 6y. I'm factoring the negative again, and divide both sides by xz. And lastly, lambda equals to, and again, factor out the negative, 6y plus 8z divided by xy. Okay, how are we going to solve? How are we going to get rid of lambdas here? So in the previous case where we have only two equations containing lambda, we easily put the two equations together because lambda equals a quantity and lambda equals a second quantity. Then by transitivity, then in this case, the two quantities are together. But in this case, how do we deal with this? Well, here we would have to combine the equations together. We have to come up with two combinations. So here you have three possibilities. Number one, you could combine 1 with 2 and 2 with 3. Or you could combine 1 with 2 and 1 with 3. Or you could combine, I think those are the possibilities. Oh, wait. 1 with 3 and 1 with 2. I think there's a total of 6 different combinations, right? If we're choosing 2 elements at a time, right? So that's a statistics problem, if you will. But anyway, we need to look at that. Okay. So I'm going to set the first two equations together. That is, this quantity equals to that quantity. But do you see how both quantities are negative? How about I just get rid of the negatives, okay, to save time. So that is 2y plus 8z over yz equals to 2x plus 6y over xz. And over here, negative 2x plus 6y over xz equals, what was that? Oh wait, get rid of the negatives. 6y plus 8z. So let's solve this equation. Oh, they look like non-linear, linear-ish with 3 variables. So that looks crazy, but don't worry. Yes, I think the 6, right? It's 6c. This one. Yes, this one right here, right? Yes. Yep, 6z and z. Thank you. Otherwise, it would have been a mess. Yes, you're right. You're right. Thank you. Thank you. Yeah, because it's all yz's, xy's, xz's, yz's. Yeah, they have to be pairwise. Yeah, thank you. By side. All right. Yeah, cross multiply. Don't be scared about these equations. They're going to simplify really nicely. Yes.
The variable that nested on the end is where.
Which is, yes, okay. This is supposed to be x in this one, right? X and x, right? Yeah, thank you. Okay, cross multiply the equation. Cross multiply, cross multiply, cross multiply, cross multiply. That's going to leave us with the following. Okay. So xz times 2y plus 8z equals to x, or rather yz, times 2x plus 6y. Okay, let's distribute to get 2.
That's also 6c.
Which one? 6. Z. Oh shoot! What was I looking at? Z. There you go. Oh yeah, right here and right there, right? Oh, thank you, thank you. Nice catch. Okay. So that'll be. Is that a Z, right? Yes, this one is gonna be a Z. Yeah. Okay. So that equals, okay, 2xyz plus 8z squared x equals to, what's that? 2xyz plus 6yz squared. All right. So, okay, the nice thing about this, 2xyz are both on both sides. We can cancel them out. And 8z squared x equals to 6yz squared. Well, we could divide out the z squareds, you know. So in this case, that's going to leave us with 8x equals to 6y. And let me do the following. Let me get x in terms of y. 6y over 8, which equals 3y over 4, or 3/4 y. Alright? Let's do this for the same for the second combination of equations. That is, xy times 2x plus 6z, xz times 6y plus 8x. So, 2x squared y plus 6xy equals to 6xyz, or 6xyz right here, and plus 8x squared z. And again, see how 6xyz goes away, 6xyz goes away, okay? So 2x squared y equals to 8x squared z. We can divide out the x squareds, right? And that's going to leave us with 2y equals to 8z. And I'm going to write the z in terms of y. So in this case, notice how the end variable, when we simplify these two equations, the common variable is y. So that's the variable you want to write these equations in terms of. That is z in terms of, that is 1/4 of y. C in terms of y, x in terms of y. Why is that? Because, oh, now we may go about, we'll go back. So okay, number one, let's call this 5 and 6. So, substitute 5 and 6 in, what was that? Number 4. Because, check equation number 4. We have x, y, and z. So we just wrote x in terms of y and z in terms of y. So we're going to get an equation that depends only on y. So that is, so x, y, z equals to 12,000. I'm going to move the 12,000 to the right at once. So x, which equals 3/4 y times the y by default, times z, which is 1/4 y equals to 12,000. Okay, let's simplify the equation before solving it. So that is going to give us 3/16 y cubed equals to 12,000. And multiply both sides by the reciprocal of the coefficient 16/3. 16/3. Okay, that's going to divide out the coefficients. That is going to leave us with y cubed equals to 12,000 times 16 divided by 3. That's going to give us a nice number, 64,000. And y equals the cube root of 64,000, which equals 40. So what do we have? We have y. We may already backtrack to the equations 5 and 6 to find the values of x and z. So we're pretty much done with this problem. So that means, okay, so x, which is 3/4, the quantity y which we just found, 40 over 4, that's 10, times 3, that's 30. And z equals to 1/4 y, which is 1/4 times 40, z equals to 10. So in this case, critical point so the critical point will be 30, 40, 10. So that's the critical point. Now we need to find, again, the minimum, right? We need to find the minimum, so we need to substitute this critical point, x, y, and z, in the corresponding variables in the original function. Well, which is the original function? The objective function, not the constraint. Careful. So f, not g, f of 30, 40, 10, that equals, okay. So that'll be 2 times 30 times 40 plus 6 times 40 times 10 plus 8 times 30 times 10. And simplifying all this madness here, that's going to give us 7,200. That means the point that will give us, in this case, the minimum is not going to be an order triple like with functions of 2 variables. For a function of 3 variables, 3 independent variables, 1 dependent variable, that's going to be an order quadruple. That is 30, 40, 10, and 7,200. Well, you might wonder, what does that mean? I mean, if you look at the function we just worked on, that looks similar to the word problem we did with the minimizing the, what's it called, the material given for a given volume, right? Okay, let me try it and make a picture for this problem. Okay, so what do we have? Maybe this is a rectangular box. All right, whose volume x, y, z equals to 12,000 units. Could be inches, feet, I don't know, yards, whatever it is. Okay, so x, y, z. So we have two xy's. That is, we have the floor and the roof. You guys agree with that part? Okay. What does the 6yz mean? Okay, yz, that'll be 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, right? The 2 sides and 5 and 4 in the middle, right? I think I should do 1 less, right? So that's 1, 2, 3, 4, 5, 6. What about the 8xz? How about this? 1, 2, 3, 4, 5, 6, 7, and the top 8, right? So all 8. So that looks maybe like a parking lot, right? Maybe you are using this function to design a parking lot that is subject to a volume of 12,000, not feet, maybe yards, I don't know. Because I mean, at a scale for a parking lot, we need a larger unit, you know, or a unit that denotes a larger dimension. And you as an engineering, as a civil engineering or an architecture, you're designing this parking lot to have how many stories? Like 1, 2, 3, 4, 5, 6, 7, 8, 9 stories. All right, and with 1, 2, 3, 4, 5 lanes or lines to park the cars, maybe, with the constraint that it has to be within 12,000 units of volume. All right, so that could be an application of this problem. Okay, let's do another application problem. Well, so a very classical problem is, and well, the quiz will have a similar problem. So find the point on the plane that is closest to the point 1, 1, 1. Okay, that's it. Okay. So they're asking us to minimize the distance because, I mean, closest means small distance. So they're asking us to minimize the distance. Okay, and they're not giving us any, what's it called? They're not giving us any objective function. They're just giving us a constraint. Be careful because that equation that does not contain an f of x y or f of x y or f of x y z notation, that's only a constraint. We need to come up with the function ourselves. What's the distance function? Well, so the distance function, that's d, using the distance formula. D equals to the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Okay? Alright, what's the picture here? Okay, so we have a plane. Okay, we have this plane, and we have in the middle of nowhere the point 1, 1, 1, right? Of course, this plane will have infinitely many points, right? So any of these points, I mean, we can find the distance between any of these points on the plane to the point that it's out of nowhere, but we want the closest one. Which one is going to be the closest one? The one that it's forming a line that forms a 90 degree with the plane. Because of course you can find also this distance right here, but that's a longer distance already. All right. So the shortest distance is this distance that forms a line with a 90 degree with the plane. But we're not going to use the angle at all. So that means this is just some random point that I'm going to call x, y, z. So the idea is to find the distance between that point and the given point 1, 1, 1. D equals to the square root of x minus 1 squared plus y minus 1 squared plus z minus 1 squared. All right. Okay. Yes. Look at this function. Did you feel like doing a chain rule with this big radical when it comes to finding the partial derivatives? That looks like a hell, right? We're not going to do that because you might remember from Calc 1 that when you run into this special case that is maximizing or minimizing a distance, so rather than optimizing the radical function, it's more than enough to simply take the square on both sides and call this uppercase D and simply work on the inside of the radical, that is with the radicand. Okay, so let me give you a brief description of the trick. Minimizing the radical is the same as minimizing just the radicand. Alright, it's the same as just minimizing the radicand, which is easier. Come on, take the partial derivative of these polynomials, way easier, alright? So, and in this case, I'm using a different symbol. Instead of doing d squared, I'm going to change it to uppercase d, because otherwise I would have to use an implicit differentiation, and you don't want to complicate the problem, right? Add more variables. No, not really. All right, so this is our objective function finally. Now let's set up the Lagrangian, that is big L of x, y, z lambda, that is the objective function x minus 1 squared plus y minus 1 squared plus z minus 1 squared plus lambda times the constraint. The constraint is going to be given by this, that is x plus 3y plus 2z minus 13. Okay? So now we have a function to work with. Let's find the 4 partials and solve the problem. No, it's not going to be as bad as the previous problem. Well, maybe a little bit. Yeah, I'll take it back. Yeah. Okay, let's find the partials. Let's get the partials. So, with respect x, mini chain rule, 2x minus 1. Minus 1. And 0, 0. Okay, careful. The partial with respect x is 1 times lambda, just lambda. Set it equal to 0. Lambda L with respect y, that equals 0, mini chain rule, 2 times y minus 1 squared, plus the derivative of 3y, which is 3 times the lambda in the front, that equals to 3 lambda equals to 0. Okay, so with respect z, that equals 0, 0, 2 times z minus 1 plus lambda times, or rather, the derivative of 2z, which is 2 times lambda, that is 2 lambda. Alright, set it equal to 0. And the derivative with respect to lambda, that's the fourth one, that equals lambda, which is 1, the derivative of lambda, which is 1, times the constraint, that is x plus 3y plus 2z minus 13. Okay? Set it equal to 0. Oh, yes. So how about this is 2x minus 2. Okay. 2x minus 2 plus lambda equals 0. The second equation. Oh, this is not supposed to be squared. All right. This is 2y minus 2 plus 3 lambda equals to 0. And lastly, 2z minus 2 plus 2 lambda equals to 0. So in a similar way, we combine the 3 equations pairwise. We're going to repeat the process. But these equations are a little bit less harmful than the ones in the example we just completed. Right? Okay, let's go for it. Solve for lambda in the 3 equations. So that is lambda equals to, how about, okay, 2 minus 2x, 3 lambda equals 2 minus 2y, and 2 lambda equals to 2 minus 2z. Okay, the first one is solved for y already, for lambda already. Here lambda equals to 2 minus 2y over 3, and here, how about we divide everything by 2? Because we can. 1 minus z, okay, much better. Alright, again, you have different options to combine the equations pairwise. So number 1, the first one with the second one, the second one with the third one. But did you see how simple would it be to combine the first one with the third one? Because there's no denominators. Let's take advantage of it. Okay, so let's do that one first, okay? And then for the other combination, I guess there will be no way around. So we will have to go with fractions. So 2 minus 2x equals 1 minus z. Okay, so here I'm going to solve for z. So negative z equals, subtract 1 from both sides. That is negative 2x plus 1. Okay, or 1, yeah, negative 2x. Okay, let me solve for z. That is z equals to 2x minus 1. So I'm getting z in terms of x. And then I'm going to combine the first one with the second one, because I would like to write y also in terms of x, right? That way we write x, that way we write y and z in terms of x to go back to the constraint and easily get the critical points. Okay, so 2 minus 2y, whoops, equals 2, oh wait, 2x equals 2 minus 2y over 3. This is really over 1. Cross multiply to get 3 times 2 minus 2x equals 2 minus 2y. That is 6 minus 6x equals to 2 minus 2y. Okay, because we already solved z in terms of x, I'm going to do the same. I'm going to solve for y in terms of x. Okay, so that's going to be subtract 2 from both sides. That's going to leave me with negative 2y equals to 6 minus 2, which is 4, minus 6x. And divide both sides by negative 2. That's going to leave us with y equals to 4 over negative 2. That's negative over negative. It's positive. That's a 3x minus 2. And we have everything we need. That is technically our equations. What was that? 5 and 6, which we may combine into equation 4 right here. Right? So we're going to replace the z in terms of x and the y in terms of x as well. That would allow us to get the first part of the critical point, the x-coordinate of the critical point. Okay, what's next? Substitute, right? Yeah. So that is x plus 3y plus 3 times y, which is in terms of x, 3x minus 2, plus 2z, which is in terms of x, 2x minus 1, and I'm going to move the 13 to the right hand side. Alright? So, okay, that's x. That's just a linear equation in terms of x, plus 9x minus 6 plus 4x minus 2 equals 13. Just combine like terms, so 9 plus 1 equals to 10 plus 4 equals to 14, and negative 6 minus 2, it's negative 8. That is 14x minus 8 equals 13. And okay, add 8 to both sides. That is 14 equals to that 21, and divide 14x and divide both sides by 14. We get 21 over 14, which reduces nicely because they're both multiples of 7. It reduces to 3/2. All right. So we have the x-coordinate of the critical point. Let's backtrack now. Go back to equation 6 to find y, and go back to equation 5 to get z. So y equals to 3 times the x value we just found, that is 3/2 minus 2. Y equals to 9/2 minus 2, which reduces to, according to my notes, this should be 5/2. Right? Oh, box it. And lastly, for z equals to 2x, which is 2 times 3/2 minus 1. Oh, integer, nice. That equals 3 minus 1. That equals to 2. Okay? So, the point on the given plane closest to 1, 1, 1 is the point 3/2, 5/2, 2. That finishes the problem. How about we look at a visual of this, of course. Okay, I'll give you a few more seconds to finish writing it down. Let me see, did I write a program? Okay. Okay, let's see. Okay, GeoGebra. Pretty graphics. Let me get rid of this plane. And let me type the equations here. Okay, so what do we have? The plane given by x plus 3y plus 2z equals to 13. All right, so that's our plane. And what else? So we're given the point 1, 1, 1. So that's the point that it's not on the plane, and we want to find the distance below. We want to find the point on the plane that is closest to that point. And of course, I can go about that point, but those are long distances. Again, we're looking for the closest, which is the one that forms pretty much a 90-degree angle. Well, let's see if the result we got it's actually on it's actually on the plane. Okay, so let's see. Let's plot the point. What was that? 3/2. 5/2. And what was the last one? 2, right? Oh, yes, it's a point on the plane, isn't it? You see it? Let me see if I can do segment, point to point, point A to point B. Did you see that 90-degree angle forming with that line or that segment containing the 2 points in the plane? So that's actually a good way to verify our work. How about that? Right?